Now, let's look at these two conductors. Both of them are spherical conductors, but one of them is hollow at the center. I don't know what is blue, hollow at the center right here. And everything else instead is still full. So all this is a solid sphere. Oops. Solid sphere. So now, let's imagine that inside this hollow hole at the center, we put a charge that is going to be a positive Q charge. Now, what happens to the disk? Let's imagine the disk initially had a charge of 0, so it's not electric charge or neutral. Well, what happens is that all the negative charges that are around in the sphere, or in the yes, in the sphere, will move toward the center because attracted by the positive charge at the center. Well, the positive charges instead in the sphere will move towards the outside because repulsed by the negative charge at the center, or the positive charge at the center. And it will look something like this. Now, as you can see again, in between, there's actually nothing. All the charge has been moved to either the inside or the outside. So in this area between these two circles, which would actually be equals to the whole area pretty much. So in this area right here, there is no charge. So it's again electrically neutral. So the positive, let's make it green, will be on the outside here and on the inside. Let me get rid of this function, right? And then the negative charge, so I'm gonna write 0, the red, will be right here. So we're gonna have a positive at the center. Then right after, this cause is a negative right next to positive. And then we have a neutral space. And then again we will have a positive space. So if you have a conductor, it can be any shape. Let me draw any shape. This. And then a cavity. I'm drawing a circle just to make it easier to see. And on the cavity, there's a positively or negative, in this case, that's the negative charged particles. Then on the surface, on the inside surface, there will be the opposite charge. So in this case, it will be positive charged particles. And then as far as it can be, there will be negative charged particles. Now, this makes sense because we can imagine that the closer they are together, so if a particle is very close to a negative particle, a positive particle very close to a negative particle, then the anarchist's potential voltage will be very high if they're very close. And in this case, the force of repulsion will be very high. Oh, sorry, if the two positive charges are next to each other, then they will be fighting each other and they will try to get away from each other. And that's what happens between the inside charge, inside the hole, and the charges that go on the outer side. They try to get as far from each other. And it makes sense because we want a lowest potential energy. Remember that anything will try to get the lowest potential energy. If, for example, we put a ball in the air it's going to tend to fall down because at this point right here, we will have potential energy mgh. But when it touches the ground, where it's going indeed, the potential energy will be equal to zero. So all the objects tend to get rid of the potential energy. And so do our conductors, or at least the charges on our conductors. This means that all these charges tend to get farther away from each other, if they are the same sign, and closer together, as you can see, if they're opposite sign. Because as we know, a positive charge will attract a negative charge. In this case, I'm going to draw it better, or something like this. But a charge with the same sign as the other will tend to repulse each other, both for negative and positive. That's how magnets work. That is also how these charges work on inductors. Let's take a step forward again. Let's imagine you have a conductor, a spherical conductor, to make it easy, and with a hollow center. Now, you know that the spherical conductor is actually neutral. This thing is neutral. But then on the inside, you place a positive Q charge. It means, as we of course probably already realized, all the negative charges will tend to get closer to the center. All the negative charges tend to get farther from the center. While the positive charges will tend to get farther from the center. And so on and so forth. Now, the sphere is now still neutrally charged because these two particles cancel each other inside the sphere. But it is now neutrally charged all over the sphere. If we take, for example, just the outside, we know that the outside will be positively charged, but the inside now, it will be positive charged. So now let's try to find the surface charge on the inside, right here. Well, how can we find it? Actually pretty easily. We can look at it and think about it. We know that the electric field will be equal to these charges, and it will actually point toward the charges themselves because they're negative charges, so they're attracting. This means that the use integral of d e times dA equals to the charge enclosed over epsilon naught. We can solve it, and of course it's going to be equals 4 pi r squared equals to the charge enclosed, which in our case will be q over epsilon naught. And so the electric field at this point right here will be the normal one, so 1 over 4 pi epsilon naught q over r squared. So right now we just proved that the electric field given by the charge at the center will be pushing toward the outside, while if we are looking at the electric field given by these charges right here, they will be pushing towards the center because it's of course a negative charge. So as I was saying, when we want to find the charge at this point, or the surface charge, to be more clear, we can do something very similar. We can look at it and think about it. And, well, if you can do it by yourself, I suggest that you just go ahead and try it, as it is not hard, it's not complicated. But if you cannot, I'll give you actually a minute to stop and try to figure out. Now I'll go ahead and explain. I gave you a minute. We can see that in our case, the surface charge for our point, in this case, let's imagine this radius is A. The surface charge at point A will be equal to the charge over 4 pi and then the radius squared. Now, how do we know what is the charge inside? Well, we can look at it and think, what matters, the charge on the inside of the sphere or the charge on the surface? Well, it actually matters what is inside.